Hello, and today I want to cover conduction, convection, and radiation with you. We want to make sure we understand this. I know I talked to you a little bit about it last week, but we want to go through this again. And then you're going to use this information to design something, hopefully. All right, so there's three ways that heat can travel. And I know Lincoln Leary understands the three ways, but the rest of us all want to understand it also. Conduction, convection, and radiation. So what we want to concentrate on is how do these three ways differ? In what types of matter do these three ways work? And lastly, what are some examples of these three types of way that heat can travel? And before I go to the next slide, I also want to point out that this is not only for heat, but this is any type of electromagnetic radiation can travel this way. So we're going to start with conduction. And the thing you need to understand about conduction is it's molecule to molecule contact. You have to have things in contact for conduction to occur. So this is the only type of heat transfer that occurs in solids, is by molecule to molecule. And examples would be a pot on a burner, where the burner is hotter than the pot, and so that heat gets transferred to the pot because they're in contact. This happens when you burn your mouth when you take a bite of a hot cheese pizza in a hot water bottle, or putting a hot brick in your bed to keep it warm. We don't do that too much anymore, but people used to do that. That heat is transferred to you or to the linens because of direct contact, or an electric blanket. All of these are ways that illustrate conduction. And the next type of heat transfer is convection. And convection occurs when you have a convection current occurring. So you set up a current, and so this will occur only in liquids and gases. The convection current occurs because you have a density change in the material that's getting heated. So let's say you have a light and it's shining on a certain amount of air. Well, that air will get hot and then rise, become less dense, and then sinks, and then if it can follow through that whole cycle again. So that is a convection current, and that is how heat can transfer into liquids or gas. This also can happen in water. And that's actually how we get our ocean currents and our major wind currents. The hot air at the equator rises, becomes less dense, rises, and then it gets drawn up more or less to the North Pole, where it gets colder, and the air then will sink, and then you can get this whole convection current again. Now there's other things that affect it. The turning of the earth then is going to cause some deflection of that current, etc. But it's essentially convection currents that cause the wind and the ocean currents. It's also why you change the direction of your ceiling fans. I don't know if you guys are aware of this or not, but in the summertime you want to bring cold air in, and cold air is denser, so it's going to be lower to the ground, and then as it heats up, that hot air rises. Well, when you have a fan, you kind of want that, speed up that process of the hot air rising, and so you have the fan going in one direction so that it creates a current in the room where the hot air can rise in the summertime, and then the cold air comes in and replaces it. But in the wintertime, the hot air will rise as you heat your house, but you don't necessarily want it to rise. You want it down low where you are, and so you change the direction of the ceiling fan so it blows the air down, so to keep more of that warm air down. And the last type of heat transfer is radiation. And this is the only way that heat or energy, electromagnetic energy, any type of energy, can travel in empty space where there's no matter, and that is by radiation. Radiation is also going to be the fastest because you're traveling at the speed of light, which is the speed of all electromagnetic waves, 186,000 miles per hour. or miles per second. I put that as an hour, but excuse me. Let's see if I can change this here to miles per second. There we go. And it's how we get most of our energy here on Earth. Examples are the sun's energy in a microwave oven. That's a type of radiation. Fireplace heat, we feel that instantaneously, just like we see light instantaneously. That's because it is a part of the electromagnetic spectrum. And infrared is just one part of the electromagnetic spectrum. The infrared radiation is what we consider heat, but all electromagnetic radiation is lumped together for as far as their speed goes, and that's what we mean when we say energy. It's not just heat, but it's energy in general. All right, so we have some pictures here, and we'll look at them and I see if we can identify the type of heat transfer I was thinking of when I put them on here. This one is a picture of a looks like an elliptical galaxy, and so I'm thinking radiation here, so I'll put a great big R here. Okay, we can see that light and any energy it's given off because it's traveling to us through empty space. Okay, and then here I have a map of the ocean currents. No, excuse me, these are the wind currents of the globe. And you can see how they kind of get drawn up. They're going to heat up and rise, and then they'll sink. And so they make this. Here we have a circular motion. Here we have another one. Okay, and that's all caused by convection currents. So this is convection. So I'll put a CV there. This is a pot of actually boiling sugar water when I think I was making caramel. So this again is a liquid, and when you boil, you know, the bubbles rise to the top. It's probably, then we go down here to on one of my cats, Sandy and my dog Belle, and they're laying against each other and getting warmth from each other. So this is contact, solid to solid, so we're going to call that conduction. That's conduction. And then here is a diagram of the interior of the globe. And we might be able to talk about a few different types of heat transfer here. If I can go back. And that is here in the underneath the crust. So here we have the crust of the earth. And then we have the mantle is right here in red. And the mantle actually has convection currents with it, which are not going to show up because it's red on red. But these convection currents occur in the mantle. Let's see if I can change my pen color here. Make it yellow for a second. Okay, so we have these convection currents here, and that's what our plates really ride on. These crustal plates, okay, move along these convection currents. That's why they collide into each other. And of course, this would be, so this is convection here. And in our greenhouse effect, again, we're getting energy from the sun. So this would be radiation here. All right, now we're ready to go to the next slide. So the last thing I'm going to talk about is insulators and conductors. And an insulator, you want to interfere with that energy travel or that heat transfer. So you have to think of, okay, how can I slow down the heat transfer? How can I stop the radiation or possibly reflect the radiation or interfere with the radiation or the convection or the conduction? Okay, and that's what you want to think about when you're trying to insulate something. Or on the other hand, if you want to transfer that heat energy, what's going to be a good conductor? What's the best way to do that? Okay, so we have insulators are things like air, and that's why down clothes are great because there's a lot of air in those feathers. The styrofoam, glass is actually a pretty good insulator of heat. And conductors is metals. Metals conduct the heat very well, and anybody who's held on to hot iron or something like that understands that, yeah, metals can conduct. You don't want to touch a hot stove that's made out of cast iron. You know, it's hot. So I put down just one conductors. I'm sure you guys can think of some others too. Hey, hope you enjoyed this and took good notes. Remember, you can pause a video anywhere you want to, and you can backtrack and rewatch certain things.